Right, so I think this is the first set of in-class exercises. Essentially, try to practice depth-first search and breadth-first search. Okay, so let's see how it goes. So graph is very different from tree. So for tree, the traversal always begin from the root node. You don't really have other choice. But in the graph, everybody is equal, right? All the nodes, they don't have a designated rank. Say that, okay, this is absolutely the beginning node. Unlike the tree case. So you have to be very careful, right? So where is your traversal's beginning, right? So in this case, we specify the beginning to be S, right? So that will be the beginning node. So the rules of the depth-first search traversal says that you try to reach out, and whichever node that you reach first, you'll try to reach from that point on, that becomes the new reaching out point, right? And from that point, you try to look for the next point that you can reach to, right? You continuously do so until you cannot do it. Then you begin to backtrack and look for alternatives. So starting from S, you have two nodes, A and C. Usually, if there's no specification about how we can choose the next node, we will follow the natural order. Natural order means that if there's a number, then we use numerical order. If it's an alphabet, we just simply follow alphabetical order. So in this case, from S, you have two options. You can go A, you can go C. So we will go for the first node, which is A, right? So you can mark it to indicate that this is done. And from A, you can actually go to B and C. So again, you follow alphabetical order. You pick the first one that you encounter. And from B, right? So now, again, you try to reach out, right? There's only one choice, which is to D. And from D, again, only one choice, you can go to G. All right, so now you have reached the end of the current path. Nowhere to go. So we will follow this recursion tree over here to backtrack, right? So we cannot go anywhere from G, so we go back to D. Try to look for alternative. Again, from D, there's no place you can go to. You go back to B, we go back to A, right? Once we reach A, we discovered that we have not visited C yet. So we will visit C from A. But once we reach C, we can see that, okay, so we can visit potentially D and G, but both D and G have been visited already. So we will not visit the same node for the second time. So we're going to terminate our search over here, go back from C to A, and then from A to S. Again, you see that when you do the backtracking, always see whether or not there are other alternatives. If you have, then you will start a new branch of the search. But if you don't, then you terminate your search, right? So in this case, this is the termination. So if you label the visit sequence, it will be 1, 2, 3, 4, 5, and then 6, right? If you want to write down this particular sequence as a single line, you can also do so. It's going to be S, A, B, and then D, G, C. This is our DFS sequence. But we still have the second way, which is to actually use the whole table together with the stack to trace the execution of this exactly the same graph. So we expect that we should generate the same sequence, right? So let's see how to do this. Okay, so the first node that we're going to process is still the S. So this is the first action. We push the candidate nodes into the stack. And then starting from each and every step afterwards, we will first pop the element. This S will go out from the stack. And the moment that we pop up the element, we will visit that element immediately if that element has not been visited yet. So after we have popped up this element, we will push in the candidates into the stack. Stack is the holding place for the element. We have A and C, but remember, right, because we want to follow the alphabetical processing order. It means that when we push the element into the stack, we cannot just follow the alphabetical order, because if we do so, In this case, A will go to the bottom and C will stay at the top. So when it comes to the next round, then C will be processed the first. This is not what we want, right? Remember, what we want as a result is that we would like to follow the natural order whenever possible. So we have A and C as the next node. We want to follow the alphabetical processing order. So when we push the element in, we have to inverse the order in which we push the elements. So instead of pushing in A followed by C, we will push C first, followed by A, inverse order. Right, so later when we go back to the code, then you will see that's the reason why when we do the loop, we loop from the end of our agency list, right? Because we want to do this inverted insertion. So C will go to the bottom, and then A will stay at the top, right? So you see the benefit of this immediately become clear when we reach the step number 2. We pop the element out. Now A will be processed next. A has not been visited yet, so we will visit A. So this time you can see that C has not been visited actually. Yeah, shouldn't cover it, right? So the only node that has been visited is S and A, right? So when it comes to the turn for A, you actually have both the C and B. So if you want to push element in, C is still eligible, right? It's just that now if you examine the content of the stack, you have 2 copies of C. This is allowed because at the moment, when we push in the second copy of the C, the first C is not processed yet, right? So from the graph's perspective, C is not visited yet, okay? Right, so B now is at the top. We will pop it out as the next element to be processed. And then we visit this node. From B, we can go to D. So we push D in again, right? So you can see that now this becomes clear why we want stack, right? Because when we have the stack, all the new element we encounter will stay at the top. So we'll just keep expanding the element that's at the top. That's how you reach deeper and deeper. So we pop D out. And then from D, we can go to G. We have C, C, and G, right? And then G is being popped out and visited. So now we have nothing to be pushing, right? So it's just C and C. And then you can see that we finally reach C, right? So we can process C and visit that. Again, you can see that C can potentially visit D and G, but D and G has been visited before already. So nothing will be done over here. We still have a copy of the C inside the stack. We will do nothing to it except just popping it out. Cannot visit that because C has been visited previously already. And the stack become empty, and this is the end of the process. Okay, so when we are at the end of the process, the stack become empty, then we terminate the DFS. What we do is that we look at this column over here, the visit column. This is our visit sequence, right? So we'll write it down as our final DFS by stack, right? If we do it correctly, it should be exactly the same as the previous version, which is done by recursion. So it's S, A, B, D, G, and then C. All right, so this is DFS tracking. The first thing you will notice is that we compare to the DFS version, we have 1 column less, right? Because for BFS, the visitation and the in-queue into the queue happen at the same time, right? While in the DFS, if you recall in the previous table, we actually separate the action of visit and the pushing, right? And the second difference, of course, is that the data structure that we use to hold the element is queue. Because this time we want to finish the current breath before we move on. So because of that, we want first in, first out, right? First comes, first serve, in other words. Again, for queue over here, this is linear data structure. So we want to have a very clear orientation. Just for your own reminder, you can say that, for example, the beginning of the queue is the head, and then the end is actually the tail, right? So that will help you so you don't get confused over time. So we still start with S, right? So we dequeue the first element, and then from S, we can go to A and C. So you can say this time, because we have a queue, it is first in, first out. When it comes to pushing in the element into the queue, we do not need to do the inversion of the order anymore. This is unlike the stack. For stack, due to the fact that you have last in, first out, you need to inverse the order in which you push in the element. But for stack or for queue, we don't need that. Okay, so A will go in first, followed by C. So this is our stack after the first step. And then remember, this is the queue after the first step. So remember, this is queue, right? So when we remove the element, you remove the element from the head, right? So A will come off first, and from A, so now you can see this time you can go to B and C. B will be in, but C will not, right? Because C has been in queue in the previous round. And remember, visit actually happens together with in queue, right? So C at this particular point is considered visited already. So the second time you are seeing it, I'm not going to insert this one. So you have C, you have B now, right? So now we can process C. And from C, right? So now we have a S, A, B already. From C, you can go to D and G, right? Both, you can check, both are not visited yet. So you can put it in, D and G. So now we have B, D, G. So if you look at this center column over here, all the nodes by this time have been visited already, right? But for completeness, you still have to do the processing to clear the queue. So B will be dequeued, but you do nothing because every scene has been visited already. You have D and G, you remove D, and then finally you remove G, right? So if you want to extract the visit order, you can either look at the center column, just straighten that, or you can also look at the DQ column. They will produce exactly the same sequence. Right, so the final sequence for BFS as a result will be this sequence over here. You just write it in a single line, SAC, and then B, D, and G. All right, so this is BFS. The final takeaway point, just a little bit of elaboration. Why? Again, why this is called breadth first, right? If you look at this graph, right, the structure over here, and then you look at this BFS sequence, we can actually slice and decompose this sequence into three parts. S, of course, this is the beginning point. So you do not need to make any extra effort, and you can already reach it. So this is with a zero effort. But if you look at A and C, both nodes require you to reach out by one edge. Right? This is like one hop. You just jump one time, and then you can reach A and C, right? So this is one hop. And then if you look at B, D, and G, right? They are not visited in one go, right? You can see that we use two different steps to reach it. But if you look at B, D, and G, all of them actually require exactly two hops. So for example, B requires you to go from S to A to B, two hops, right? D is going to be S to C to D. And then G is actually from S to C to G, right? So this is why it's being called the breadth first search, right? So we increase the breadth one at a time and see how many nodes we can visit at that breadth, right? So you can see this is 0, this is 1, this is 2. And you can, if you have a larger graph, you can even have like 3, 4, 5, so on and so forth. Right, so as illustrated in the class example, we need the stack. Right, later we'll explain why we need a stack. right? But this particular step will help you hold any point that you cannot expand any further. The reason why whenever you cannot expand any further, you push it into the stack is to say that if you cannot expand any further along the DFS, what it means is that nobody will be depending on you, right? So whenever this point has been reached, I already ensure because I execute DFS and I cannot go anywhere. It means that nobody will be depending on me. So at this point, it's actually safe to execute this particular node, right? So pushing a node that you cannot expand any further into the TO stack means that. Right, so again, you have many different nodes, which means that if you want to execute this topological sorting, there's a lot of possibility. But as always, if there's no obvious choice, we will just follow alphabetical order or numerical order, right? In this case, we'll try to start the DFS from 2, the smallest number, but 2, yes, you lead to nowhere, right? So immediately this DFS ends. So 2 will be pushed into the TO stack, right? And then we start from the next number, which is number 3. From 3, you can go to 8, right? From 8, you can go to 9, right? So now you can see that at the point that you reach 9, you cannot go anywhere, right? So this is basically indication that nobody will be depending on 9. So it's actually safe to push 9 into the stack, right? And then you backtrack to 8. Again, the answer is the same, right? Nobody depends on 8. So you push 8 into the TO stack. And then you are going back to 3. This time you do have another alternative node that you can go to, which is 10. But from 10, again, you see this is dead end, right? Nowhere to go. So I push in 10. So now I'm finally back to 3 again, and this time I have exhausted all the candidates. So I will remove 3, push it into the TO stack. So I look at the graph again. I look for the nodes that has not been visited yet in sequence. The next node in line will be number 5. And 5 can go to 11. And then 11 can go to 9. But 9 has been visited already, right? So we do nothing, right? So remove 11, push it into the stack, return back to 5. Again, nowhere to go from 5 now. So you push 5 in. We still have a final number. Don't miss it, right? 7. Again, this is a relatively isolated number. You only have a single number, but still you need to write it out and push it into the stack. Right, so 7 is actually the last number, right? It doesn't depend on anybody. So when it comes to the construction of the final topological order, we're going to pop out all the elements one by one. So in other words, this is our recommended execution order, right? This is the order of the sequence from the top of the stack to the bottom of the stack. Right, so if you just write it out, this is your topological order. It's going to be 7, 5, 11, 3, 10, 8, 9, and then 2, right? So the final step, as we illustrated in the class example, before you report this answer, right, you can do a final check. And the way we check it is that we write down the topological order. As a horizontal line over here, right? This is your execution order, right? From left to right. So now the next thing you do is that just follow this order, try to reconnect all the edges. If this order is correct, it means that all the prerequisite should be finished at the left-hand side. Prerequisite should never happen in the future, right? Because if prerequisite happen in the future, it basically means that you try to execute a task while without fulfilling the prerequisite for that task, right? So translated into the graph term, right? This is the reason why we want to see all the edges pointing forward. It cannot point backwards, right? Because if you point backwards, it means that your dependency is actually not fulfilled, right? So let's see how it goes. For 7, for example, the dependency goes into 8 and 11. 8 and 11 actually depend on 7, right? So we connect the link, 7 to 8, and then 7 to 11. Right, so this is 7, and then we move on to 5. 5 is connected to 11. Okay, so now you see what we mean, right? So 11, actually, if you look at this graph, 11 depends on 5, 11 depends on 7, right? So before you reach 11, you should definitely see 5 and 7 already. But if you do not, right, means that 5 and 7 appear after 11, then the edges will be pointing backwards, right? So this is what I mean by whenever you see the edge pointing backwards, you are violating the dependency requirement. Okay, so we are now at 11. 11 lead to 2, 9, and 10, right? 10, 9, and then also 2, right? So far, so good. And then number 3 lead to 8 and 10. 10, 8. And then 10 lead to nowhere. 8 lead to 9. And then 9 again lead to nowhere. The final check, don't forget, like 2, whether or not there's any link going out, 2 is a dead end. So there's no link, right? So based on this check, all the edges are pointing forward. So our execution sequence, because of that, is correct, right? So this is the valid final check. This is a valid topological order.